Corporation. I'm Southeastern Regional Manager and South American Regional Manager. And today we're going to talk a little bit about the history of 3D printing as it relates to Z Corporation and the history in general. Talk a little bit about how 3D printing has gone from a want-to-have to a must-have in industry, and how industry is using it today, and which ties into why it's important to have 3D printing in education these days. And also we'll go into the criteria for purchasing a 3D printer. There's 3D printers have become very, very popular over the last few years, and there's a lot of misinformation and confusion and just a whole lot of information out there that's hard to sort through, and it can be very confusing when you purchase a 3D printer. So because we sold so many systems to educational facilities, we've boiled down some criteria that we've seen most schools and school systems look at when purchasing a 3D printer, and we'll go over that for you as well. So just a quick history of ZCorp, who we are, where we came from, and also in the 3D printing industry in general. We were the first 3D printers out there, really. The technology was developed at MIT. In the mid-90s, some of the professors that developed the technology broke away from MIT and teamed up with some people who had some money, and they formed Z Corporation. In 96 or 97, I believe we sold one system. 97 we sold, I think it was 7, or 98 we sold 7 systems. And now we're selling well over 1,000 systems a year, typically. We introduced the first full-color printer in the market in the year 2000, and we have an install base. This should be updated. It's more. I think it's more than 6,000 systems worldwide now. So how does 3D printing work? In general, you start off with a 3D solid model, and probably 60, 70, 80% of the time that solid model comes from a CAD source like SolidWorks, Pro-E, Inventor, it's 3D Studio. But you can get that from a lot of other sources as well. A lot of people aren't aware that you can get data from satellite imagery data. You can get data from CT, MRI scans for medical applications, where you can literally build your own skull if you wanted to. You can get data from 3D scanners. You can get data from video games. There's a lot of people building their own avatars, and we have some examples of that back in our booth. But wherever you get the data, we take that data, and it needs to be in a solid model format. And we take that data and we slice it into 3,500 layer thicknesses. So our software, the driver to our printer, does that automatically for you. You guys don't even know it's happening. But that's the first thing it does, and our software is called ZPrint that goes into the system. Then we take that data layer by layer and we send it to our printer. And the way the printer works is really very simple. It's very similar to a 2D printer. But instead of using paper, we use powder. Instead of using ink, we use a glue. So what we do is we lay down a thin layer of powder, 3,500ths of an inch thick, and then that gantry that laid down that powder is going to come back across, and there's a little print head, just a standard HP print head in there, and we feed it a binder fluid or a glue. And that print head, all it does is it draws a cross-section for that particular layer that we just talked about, where we slice those layers, into that powder, selectively solidifying that powder and turning it into a solid. That platform then drops again, and then the second iteration takes place. So you're literally growing the part layer by layer. And what happens at the end of the build, you can imagine, so you got this part of solidified powder inside the powder, and then you got all this other powder surrounding it. Well, we evacuate that powder through vibration and suction to the bottom of the machine. And our technology is very green. We're able to take that powder that we didn't use to build the part, filter it, recycle it, and put it right back into the machine and prep it for the next build. So what you have left in the bottom of the build chamber is your part that you sent to the machine earlier in a solid model format. 3D printing, again, has gone from a kind of a nice to have to a must-have these days. You know, back when I got into this industry 15 years ago, you never heard about 3D printers or rapid prototyping outside the engineering community, and there was a whole lot of engineers who didn't even know about it. So it's kind of starting to evolve outside the engineering community and getting more recognition. You can see that it's in Fortune magazine, The Economist, and you can see a lot of articles about Z Corporation in these magazines, but also within the standard trade journals that you would see within the engineering, product design, development community. So we'll talk about now the adoption of 3D printing into industry. If you see any industry research done recently that talks about product development engineering, you'll see that 3D printing is typically in the forefront with CAD systems. We'll also talk about how leading industrial design firms, there's a lot of companies that outsource all their industrial design and engineering to outside firms that handle this. And we'll see how a lot of those firms utilize the technology. But also talk a little bit about how industry uses it, where they use it. It's used all across the board these days, but again, mainly in product development and engineering. Aberdeen Group is a group that performs a lot of studies out there in industry, and Autodesk and PTC, I'm sure you guys recognize them. They're two big CAD companies out there on the market. They paid the Aberdeen Group basically to analyze the whole product development market and see what people are doing, how they utilize technology. And a quote from their study is stated that the best in class are twice as likely as lagging organizations to take advantage of 3D printing and rapid prototyping. Basically, if you're not involved and have 3D printing in your company now, you're not going to survive, is what this study came up with. And another way of putting it is basically the companies that have this technology are able to hit their targets in not only cost savings, but also in time to market. And in this world, as things need to come to market faster and faster, and things need to be done faster and faster, not having a critical tool like this in your product development engineering department is crazy. IDEO is one of the leading industrial design firms out there in the world, and this is just a little slide describing how they do their design process. IDEO is a big believer in prototyping and 3D printing. Prototyping is the language of innovation and way of life at IDEO. Prototyping is the problem solving in 3 dimensions. And prototyping lets you fail early to succeed sooner, and that's what we see a lot out in industry today. We always talk about prototype early, prototype often. The reason being is, and I'm sure you guys have seen, anybody who's taken an engineering course or studied design development, when you do, come on in, I scare them off. When you do design development in the concept stage, if you find an error, that error may cost you $1 or a few dollars. That same error later on in the engineering phase may cost you $100, and maybe down in tooling phase they may cost you tens of thousands of dollars, and in production it may cost you hundreds of thousands of dollars. So why not prototype as much as you can, as early as you can, when it's the most cost effective to find that error? And with 3D printing, that prototyping is very quick and very easy and very cost effective to do now. Used to, it cost a lot of money to make prototypes, but now with 3D printing, everybody's in the design development community is utilizing it up front to figure out those errors in the design iteration process, and where the errors are the most cost effective to find. So who's using the 3D printers throughout the world? Basically, anybody doing product development, design, engineering. Anybody from consumer products, electronics, to automotive, to aerospace, to medical, to Disney's got it to develop their rides and also to do some of their animatronics. It's a diverse community, so it's not just one segment or one area in product development or engineering. It's all across the board. And again, you can see that this has moved from a nice to have to a must have. And that's also confirmed through the number of units that have been sold out there. Basically, in about the year 2000, things took off. And, like I said, we sell well over 1,000 systems a year typically now. And again, mainly used in product development, design, but it's also used in manufacturing. We have some companies that are making their end products with our printers. We have some emerging companies, emerging industries like architecture. They're just now starting to get into 3D CAD. They're starting to utilize the technology a lot more. Instead of having 20 interns in the back room make a model by hand for a week, why not press a button on a printer and have it built for you in a few hours? Used a lot of medical applications like we talked about, CT, MRI scanning. So there's a lot of emerging markets that are coming out there too, not just industry. So we'll switch gears a little bit now and talk about why 3D printing is important to education. Obviously, we kind of proven that industry utilizes the technology, so why is it important? Other than the obvious that we want to teach people to be prepared for industry, why do we want to have 3D printing in the classroom? One is it engages the students. Nothing's worse than having a classroom with students that just kind of hemming and hawing and not really happy about or not excited about what they're doing. What we found with these printers is when we bring a printer in the classroom, it really gets the students engaged. It really gets them motivated because now their part that they've developed on the screen goes from concept to actual reality, and they can hold it in their hands. They can do fit checks with it. They can take it home and show mom and dad. So it really engages the students. It enhances learning because now you're kind of allowing the students through prototyping to complete the whole design cycle, meaning that they go from problem to solving the problem to actually implementing the solution with the physical prototype. Now they can go through the whole design iteration process. So it really enhances how they learn the whole product development and engineering. And again, the end objective here is to teach the students, what they need to know to be successful out in the real world. And it really encourages advancement. It prepares the middle school students for high school, the high school students for university, and the university for post-grad or their job once they graduate. Got a few quotes here. When students hold parts in their hands, they're closing the loop. Until then, it's all conceptual, virtual, and 2D. Completing the circle is important to us. It turns kids on. And what we found is it's not only important that they get to a model in their hand, but it's important that you do that as fast as possible. If you have a printer and it's not able to produce a model, because it's backlogged or there's too many people trying to use the printer at once, and the student doesn't get the model for a week or two, it kind of fizzles out their enthusiasm on the project. So, and in this world today, the world of immediate gratification, it's very important that you get a model in their hands as soon as they get the design done or shortly thereafter. It really gets the students excited and gets them motivated for the next projects.
I have a quick question.
Sure.
Are these plug and play or are they network applications?
In
terms of sending a file to the printer?
Yeah, so you can have a standalone, if I'm
like a flash drive, plug it in, or is it network where you're taking your computer
Yeah.
and through a network?
Either one. So you can either plug it into its own individual computer and then bring files to that computer, either via network or what have you, or you can network these printers in. So one of the neat things too is, say you have one school system, 6 schools that want to utilize the technology, but you can only afford one. Well, you can network it in and all schools can utilize it. I won't read all these quotes, but basically, if you give a student a part, it gets them engaged, gets them motivated. If you get it, it's important that you get it to them very quickly. Not only are they does it allow them to do the basics and teach them the basics about product development design, and that they can do fit checks, form studies, and functional testing. Hey, does this thing actually work? But they can also take it and they get very excited when they show it to their friends and show it, take something home and show it to mom and dad. So another reason to buy or get a 3D printer in the classroom is it enhances learning. Again, we talked about the whole product development iterative process. What we see is that when kids really start learning the product development design process is when they do typically more than one prototype. That's when they really start learning about how things work. I haven't seen or met an engineer that was right the first go around on their design. So it's very important that they learn that usually when they design something, the reason for creating that prototype is to make sure it does what you want it to do. One of the main reasons. If they don't learn that they can use that, how to use that prototype to make changes and to instigate improvements, then they're not really learning. They just kind of stop at the design phase and then they move on. So a lot of teachers will take this, they'll bring it in and say, okay, design this cell phone, and these pieces have got to fit together. They take it out, oops, something doesn't fit together. Then they learn, okay, well, now I have to go back and I can make an improvement here in my CAD system, go through the whole iteration again, and come up with their second version of the prototype, where it either fixes the problem or improves design or both, which is what we see people doing out in the product development world and industry. So it really helps kids a lot when they complete the process. Even U.S. National Science Standards for Technology Design, this is their process for design process. And with a 3D printer, you can touch on 4 of those 5 stages. Basically, the only stage it really doesn't touch is identifying the problem. And some could argue that you could utilize it for that as well. Also, ITEA talks about making a model, prototyping, testing, evaluating, designing, refining design, making it, and communicating results. They talk about the whole design iteration process and how it enhances learning. Is this locking up on me? There we go. And of course, it encourages advancement. It's kind of a no-brainer, but we talk about it too. I mean, the end objective is we're preparing the students for industry, and the students that are doing this in high schools are more prepared and equipped for colleges, which are in turn more prepared and equipped for industry. I can tell you now, every design engineering department that's worth its weight has a 3D printer. If they don't, if I was a kid coming out of school and I went to a design engineering department, they didn't have a 3D printer, I wouldn't go work for that company. That just tells me that they're far behind. In universities, it's starting to get to where almost all universities' design engineering departments have 3D printers. So a lot of the students that are coming out of high schools are almost expected now, and I think pretty soon that they will be expected to know this technology, just like they're expected to know the basics of computers these days. Here's another quote. I hate reading these quotes, but so I'm just going to let you guys read them. But in essence, these printers prepare the students get jobs out in the real world when they're ready. About 30% of our market is education. It's pretty significant. It's very important to us at ZCorp. This is just a small sampling, but we have well over 1,000 high schools, universities, tech schools, you name it, that utilize our technology. Various departments from architectural, design, engineering, medical, all across the board. It's pretty amazing to me that we're now even selling these to middle schools. It's kind of fun to think that there's 5th, 6th graders out there drawing something up in CAD and printing it out. Especially for me, a guy that came from a high school that I think we barely have 1 or 2 computers. So again, going from a nice to have to a must have. So now hopefully I've shown you, industries, where industry is with this technology, and it's well entrenched within industry now. Why it's important for education. So for the people that are thinking about purchasing a printer, we'll talk about the criteria for that we typically see teachers looking at when they want to bring a system in-house. Again, there's a lot of information out there, and there's a lot of things to think about, but we boiled that down into a few criteria that should help you decide which printer is right for your school. So one of the first things to think about is productivity. Does it support the entire classroom? If you network it in, does it support your entire network of people that you got plugged into this? And it's just some really simple homework. It takes about 3 or 4 minutes, but it's very important that you go through some of these exercises before you purchase a printer. Because if you have a printer that cannot meet the capacity of your students, it doesn't really do the job for you. Cost is a very important thing to take a look at. And I'm not talking about just upfront cost. I'm really talking about operation costs. There's been a lot of times where we've gone in and we've seen people buy 3D printing technology, and 3 months later they run out of materials and they're done, and the machine just sits there. It's a shame. There's a lot of companies out there that have kind of what I call the razor blade mentality, where they will sell you something cheap up front, but they get you on the materials down the road, or the maintenance. So it's very important that you take a look at the entire cost from a holistic view. Model quality, you want to make sure the printer does what you need it to do. It's no good if it doesn't print out a good resolution part, or it prints out a part, or if it doesn't print out a part that to the detail that your students are drawing in the CAD system. Color is also very, very important from the creativity aspect to just plain communication for a lot of students. So that's something that you want to take a look at. And of course, classroom friendliness. You want a system that you can put in your classroom. You don't want to have it in a locked room down the hall where only certain people can use it. You want to make sure it's easy and safe for your students. And of course, responsive support. So what is a 3D printer? Basically, it's just a tool to get to your end objective, right? A part that your student can have in their hands to do is fit, form, functional testing, get them engaged, and enhance the learning process. So one of the first things you typically want to do is just do a real simple calculation. Just I've got this printer, it's going to support this many classes, I have this many students per class. Typically, because we were talking about the iteration process, you typically want to make sure that you allow for a couple parts for each student, and just calculate how many parts you're going to need to build. I'll brag about our systems a little bit in that we are by far the fastest technology and the most productive technology out there. We're 5 to 10 times faster than any other technology, but we're also very productive in that we can do what we call stack and pack. You can put a whole bunch of parts into the printer all at once because we don't have support structures. You can build it if you have enough room. You can build an entire classroom of parts, in one build. So it's extremely productive system out there, not only from the speed but from the number of parts that you can do per build. Then, along with productivity, you want to be thinking about costs, and that's just one more step in the calculation. But we understand that schools are resource constrained, especially in these days. Schools need to provide access to all students. It doesn't do any good if only 2 or 3 students can go to the printer and the rest can't, or once everybody's able to do one model and only a few are able to do 2 in the iterative process. So it's critical that you look at, again, take a holistic approach at this and look at, not only how much is this printer going to cost me today, how much is it going to cost me, 1, 2, 3 years down the road. We have programs that we've implemented for this on the materials side, where you can advance purchase materials on a credit, so you can, when you go to that well to get that money, you buy enough materials on credit for 2 or 3 years out, and we're able to do that through a program called the LEAP package, which basically allows you to advance purchase material at a significant discount, and you have a credit with us. So 1 year, 2 years down the road, you can just go to our website, say I need 3 of these, 4 of these, what have you. Which really helps out a lot, again, in a lot of situations where people are going for grants and they have a one lump sum of money. And I'll brag about our printers a little bit more. We're on the cost side of things, we're typically about 1/3 of the operating costs. Our materials are because we don't use support structures and because our materials are so inexpensive, we're about 1/3 of the costs out there. Because we recycle our materials, you save a lot of money. It's a very green technology, and then again, like I was explaining in the initial slides, through vacuum and suction, we evacuate the material and filter it and recycle. So that saves a lot of money. And again, because we can stack and pack, and because we don't have support structures, and because of our speed, we're extremely productive systems. So again, back to calculating the total number of parts. This is just a simple calculation we threw up there, but semester, class, students, saying we want 2 parts per student, we estimate 60 parts total. Then you want to take that one step further and calculate how much material you think you're going to be using. And there's a lot of people, you have to be careful, there's a lot of people out there that will say, well, I'll give you a year's supply worth of material, which is kind of a ridiculous statement, because that's like saying, I'll give you a year's worth of gas for your car. For the little old lady that goes to church every Sunday and drives 3 miles, that may be a few gallons a year, but for a salesperson that's out on the road, that can be thousands of gallons per year. So be very careful and wary of people who say, make vague, non-quantitative comments like that. What you want to do is you want to take your total number of parts and get some kind of hard number in terms of volume for how much material you're going to be using. And typically that's done in cubic inches, you can do it in cubic centimeters, what have you. But usually what you want to do is you want to pick out a part that you think is an average part. We use a baseball in this presentation because most people understand about how big a baseball is, and that's about 13 cubic inches of material. So we know that 60 parts times 13, we're going to need 780 cubic inches of material. So something else to be thinking about too is if you're looking at a technology that has support structures, you not only need to know how much material your physical part is going to take up, but you're going to have to add some material for support structures too. So you're going to need more material beyond that. But for our systems, because we don't use support structures, we use 780 cubic inches. So just an example of here, how long it takes for us to build all these baseballs. It would take 10 days. The next closest competitor, it would take 120 days. And a lot of people say, no, that's pretty significant. The difference is really there. I mean, that's not exaggerated numbers. Our material costs are typically, it can range between anywhere from about $1 to $2 a cubic inch up to about $3 or $4 a cubic inch. We use 3 as kind of an average. Next closest competitor, taking into account with consumables, they're about $7 a cubic inch. So you can see that for annual consumable usage, there's a pretty significant difference. So again, take a close look at your material costs and your productivity for each system as it relates to what you're trying to accomplish. And we go back to this slide and how many parts you build. Most systems would suffice in the classroom if you're constantly building parts. But the reality that we see in the classroom is that the printer is used a little bit during the class time, but as with any project, the students always wait to the last minute and then they do everything all at once. So you really need to have a printer that can take all those parts and put them through your system very quickly. So keep in mind that not only do you want it to be able to do a lot of parts, but in most situations you need it to be able to do a lot of parts very quickly. And as we said before, students learn by engaging in the design process. So you want to make sure that whatever you're doing, that they get a part, they get it fairly quickly. But also you want to make sure that they do at least 1 or 2 parts, so they really learn. Not only do they get engaged, but they learn the whole design iteration process. And that's where we see people really, or the students really getting excited and learning about how design and engineering works. So another thing to take a look at is model quality. Always make sure that the printer you're buying is going to do the detail you need. And a simple way of doing that is just doing a quick text block. Something you can draw up in your CAD system, raise the lettering, and just change the font as it goes down. Have all your people that you're looking at build one of these for you, and you'll see how much detail each printer can do. If somebody bucks at doing this, then beware, because there's probably a good chance that this will show the limitations of their process. In color, I have a lot of people tell me, especially in the educational community, that color is paramount. Initially, a lot of people look at color and say, okay, that's kind of nice. But it's really gone from a nice to have to a must have for a lot of, not only for industry, but for a lot of educational accounts. The reason being is it really opens up the creativity for students that are doing design and engineering work. For just plain old mechanical design, it's great to have a color part to show all the individual components, especially if you do a cutaway. For industrial design, it's great to show how you can do concept models and utilize them for focus groups. Architectures utilize it for showing different fascias for building different colors of bricks, things like that. Using chemistry for molecular modeling. Geography, you can take the satellite imagery data and do color plot charts. There's the state of Illinois over to the far right. Fine arts, animation. It's really something that's important to a lot of students. So a lot of times when you're doing a benchmark part 2, you may have something to do with raised lettering, but I would encourage you to also have the part colored, so you can see the color capabilities within the system. Come on, computer. And then classroom friendliness. You want something that's you can put in the back of the classroom. It's not going to be loud. It's going to, you want to have something you're not going to have to worry about chemicals or things of that nature. With our systems, the powder is an inert material. The binder fluid is a water-based binder. We have a lot of inert properties with our systems. Our systems are very portable too, so you can move around. If you don't want to network it in, you can literally wheel it from classroom to classroom or from building to building if you want. Plugs into a 110 outlet, and you're ready to go. So that's something else to take a look at when you're getting a printer. So I hope I showed you how industry is utilizing the technology, how it's gone from a nice to have to must have in industry, why it's critical in having it in the classroom, and why it's important that students have this for engaging and enhancing their learning process, and the criteria that most people look at when they're buying one of these systems. I know that's not much time. That's about 45 minutes. I know that's not the full hour. What did we get, an hour and 15 minutes or something like that? But I'm here for questions. We have one of our printers out on the showroom floor. Please come by and visit. We've got posters and some bearings if you guys would like a freebie to take home with you. And open it up to questions. Anybody have any questions, comments?
I just have a question on, as far as cleaning stations, we've been looking very briefly at different machines. Is there a cleaning station involved with these? Some models do, some models don't.
Depends on the systems. Our recent generation systems, it's all incorporated. So as you can imagine, when a part comes out of the build, even though the powder evacuates, you're still going to have a little powder on the side of the part. If you look down at the system that we have, we've incorporated in our recent generation systems what we call the powder recycling station. And again, when you remove that and do that gross depowdering, there's still going to be a little powder sticking on the side of the part. So you just pull the part over to this area, and it has a little air compressor and a vacuum, or it works through vacuum, and you just blow off any excess powder with our system. So that's all incorporated within it.
And there's no wet cleaning involved in it?
No. Now there is you can further strengthen the part by doing what we call infiltration. And you can either do that by spraying it with salt water, or you can have a little Tupperware container of CA and you can dip it in that and let it dry. But that all can be done within
CA is
cyanoacrylate, yeah. Any other questions? Comments?
Do you have a tabletop version?
Not yet.
Any plans?
I would be shot if I talked about our plans. But we've got some technologies now that that competes with the tabletop version. It's just not physically a tabletop. It doesn't physically fit on top of a table. And tabletops are kind of people call some of the systems tabletops, but some of them really aren't. I mean, some of them you really need to have a stand or a very strong table to put it on.
Counter.
Do what?
Very deep counter that you don't find in
Right.
typical classrooms.
Yeah. And some people...
Standard countertop's 24 inches deep. Most of those others you'll find you need a 30-inch deep counter, and it's not as countertop friendly as it may originally appear or be advertised. I guess the other thing I can say is just about the ability to use it across multiple disciplines, whether you're in a high school setting or a university setting. The ability to use it within, if it's a community college or university setting, within an engineering department, you may have computer engineering, you may have electrical engineering, you may have aeronautical engineering, and be able to take and use it in multiple applications through either a wing in the aeronautical with finite element analysis and print the actual wind as it's blowing across that airfoil, and be able to have students look and see that and notice those heat spots and the cool spots, and be able to redesign that through that whole design loop iteration that you're talking about, all the way through to the mechanical and the architecture, being able to print to it from over in their side of the house and have models. I mean, the versatility of this machine is, at least in my mind, the thing that really sets it apart. High school setting. I've got a high school that is using it between their engineering department, their engineering drawing department, their engineering design and tech department, and their business department. These kids are actually in their engineering design drawing a part. They're handing it off to the business class. Business classes are showing it at lunch or carrying it around the room, asking about feedback from learning marketing, if you will, and then they're bringing it back to the engineers who have to redesign and reiterate the part. And that's really hard to do if you can't do color and if you don't have a lot of flexibility in what you're able to design. The students cap out pretty quick. And as you know, with today's learner, they're way far past the software packages that are even out there now in what they can envision and see and draw. And to really kind of handcuff them into a certain technology or a certain not being able to do color, I really think it's kind of a disservice to them. So the versatility of Z Corporation and the line of products that they have is really unlike any others that are out there in the marketplace. It truly is.
Somebody might think you're selling them, Tom.
We do represent them, but I can tell you, I'm a technology education teacher and a member of ITEA, so it's near and dear to my heart. And to be able to see the versatility of the machine and how multiple disciplines can use it within the classroom. You know, the selling piece is just something that goes along with it. I'm in the classes working with the kids, working with the teachers, really making it happen. That's what we're going to need for tomorrow.
The fact that you're working with crossing disciplines is really critical with today's teachers, because if you sit back and do nothing, that's what you're going to get. So you're bringing in technology there, so that's great to be able to share it with others. It's the district's equipment, it's not yours.
Right, and that's one of the reasons why it's networkable, it's portable, and it's really fun and interesting to us, because almost every day I see a new application for a printer. I'll go into a school and somebody over here that you never really thought how they could utilize the technology figures out a way that you can utilize it in theater, where they'll do like backdrops for the stage. They'll actually build the and you're like, wow, I didn't even think about that. That's ironic for us, both in industry and education. In industry, there's a big justification to bring a printer in-house of ways they think they'll use it, and ways they know they use it. As soon as they bring it in, that justification is blown away because they use it for tons of different things: production, marketing, design, development, engineering, all that good stuff. And the same with education. When we bring a printer in, a lot of times, now some schools and some departments share better than others, but the ones that do share, it's encouraging and inspiring to see how they take a look at that technology and they utilize it across many different disciplines.
From a law of gravity standpoint, how does the no support structures, how does that work when it's printed without any support structure?
We have a magician down there. Yeah, it's really, the powder itself is the support. So when it's being built, it's kind of hard to see this, and without seeing the printer down there. That's why I always encourage people to come down and take a look at it, because when you look at it, you can really get it a lot better. But basically, the powder itself supports the part as it's being built. So, I mean, you can do a lot of neat things like, building the ball bearings inside of this. Because while this is being built, the balls inside of here are actually being supported by the powder and are completely separate from the outside ring and the inside ring. But when the powder evacuates at the end of the build, all the powder separates and it loosens everything up and it starts.
Oh,
So
So
it's,
you're laying down the whole layer.
Exactly.
And then you I gotcha.
exactly.
So the baseball, as it's being built, is a layer,
It's a stone.
a layer.
And all you ever really
And then
see,
it's
well,
recycled,
yeah,
the parts of the square that you don't use.
yeah, it's evacuated out to the bottom, filtered, and recycled back into the hopper.
I was picturing the glue first, putting the powder on the glue.
Yeah, it's a flip-flop,
Yeah.
exactly. Jim, question? Comments, questions? Thanks for coming. Everybody's welcome to a poster, 3-part. We even give away 2 free cards.